Ray Kurzweil discusses the future of technology.
Well, it's great to be here. We've heard a lot about the promise of technology and the peril. I've been quite interested in both. If we could convert 0.03% of the sunlight that falls on the Earth into energy, we could meet all of our projected needs for 2030. But if you ask me what will it cost for 1 MIPS of computing in 2010, or the cost to sequence a base pair of DNA in 2012, or the cost of sending a megabyte of data wirelessly in 2014, it turns out that those are very predictable. There are remarkably smooth exponential curves that govern price, performance, capacity, bandwidth. And I'm going to show you a small sample of this. But there's really a theoretical reason why technology develops in an exponential fashion. And a lot of people, when they think about the future, think about it linearly. They think they're going to continue to develop a problem or address a problem using today's tools at today's pace of progress and fail to take into consideration this exponential growth. The actual paradigm shift rate, the rate of adopting new ideas, is doubling every decade according to our models. These are all logarithmic graphs. So as you go up the level, it represents generally multiplying by a factor of 10 or 100. It took us half a century to adopt the telephone, the first virtual reality technology. Cell phones were adopted in about 8 years. If you put different communication technologies on this logarithmic graph, television, radio, telephone were adopted in decades. Recent technologies like the PC, the web, cell phones were under a decade. Now this is an interesting chart, and this really gets at the fundamental reason why an evolutionary process, and both biology and technology are evolutionary processes, accelerate. They work through indirection. They create a capability, and then it uses that capability to bring on the next, what they thought the key events were in biological evolution and technological evolution. And again, it forms the same straight line. You have a little bit of thickening of the line because people do have disagreements what the key points are. There's differences of opinion when agriculture started, how long the Cambrian explosion took. But you see a very clear trend. There's a basic, profound acceleration of this evolutionary process. Information technologies double their capacity, price, performance, bandwidth every year. And that's a very profound explosion of exponential growth. I put 49 famous computers on this logarithmic graph. By the way, a straight line on a logarithmic graph is exponential growth. That's another exponential. It took us 3 years to double the price performance of computing in 1900, 2 years in the middle. We're now doubling it every 1 year.
Logarithmic graphs disguise the true distance between points and do not show the true exponential growth that has been occurring. In the graph on the left, we see that the value of each point has been reduced by a power of 10 for each of the movements vertically on the axis. The graph on the right shows us true exponential growth. Here, each value vertically represents the actual value of the point. If we were to take a log of these points, it would look much more like the graph on the left.
And that's exponential growth through 5 different paradigms. Moore's law was just the last part of that, where we were shrinking transistors on an integrated circuit. But we had electromechanical calculators, relay-based computers that cracked the German Enigma code, vacuum tubes in the 1950s predicted the election of Eisenhower, discrete transistors used in the first space flights, and then Moore's law.
Moore's law is named after Gordon E. Moore, co-founder of Intel. In 1965, Moore observed that the number of transistors placed on integrated circuits were doubling every 18 months. This means that the cost of a computer stays the same while its power doubles. The result is the dramatic increase in computer power and the reduction in overall cost.
Every time one paradigm ran out of steam, another paradigm came out of left field to continue the exponential growth. They were shrinking vacuum tubes, making them smaller and smaller. That hit a wall. They couldn't shrink them and keep the vacuum. A whole different paradigm. Transistors came out of the woodwork. In fact, when we see the end of the line for a particular paradigm, it creates research pressure to create the next paradigm. And because we've been predicting the end of Moore's law for quite a long time. The first prediction said 2002, until now says 2022. But by the teen years, the features of transistors will be a few atoms in width, and we won't be able to shrink them anymore. That'll be the end of Moore's law, but it won't be the end of the exponential growth of computing, because chips are flat. We live in a three-dimensional world. We might as well use the third dimension. We will go into the third dimension, and there's been tremendous progress just in the last few years of getting three-dimensional, self-organizing molecular circuits to work. We'll have those ready well before Moore's law runs out of steam. Supercomputers, same thing. Processor performance on Intel chips. The average price of a transistor, 1968, you could buy one transistor for $1. You could buy 10 million in 2002. As we make them smaller and less expensive, the electrons have less distance to travel. They're faster. So we've had exponential growth in the speed of transistors, so the cost of a cycle of one transistor has been coming down with a halving rate of 1.1 years. You add other forms of innovation in processor design, you get a doubling of price performance of computing every 1 year. All of this is driving exponentially growing economic progress. We've had productivity go from $30 to $150 per hour of labor in the last 50 years. E-commerce has been growing exponentially. It's now $1 trillion. You might wonder, well, wasn't there a boom and a bust? That was strictly a capital markets phenomena. Wall Street noticed that this was a revolutionary technology, which it was, but then 6 months later, when it hadn't revolutionized all business models, they figured, well, that was wrong, and then we had this bust. They'll be so small, they'll be embedded in our clothing, in our environment. Images will be written directly to our retina, providing full immersion virtual reality, augmented real reality. We'll be interacting with virtual personalities. But if we go to 2029, we really have the full maturity of these trends, and you have to appreciate how many turns of the screw in terms of generations of technology, which are getting faster and faster, we'll have at that point. We will have 2 to the 25th power greater price performance capacity and bandwidth of these technologies, which is pretty phenomenal. It'll be millions of times more powerful than it is today. We'll have completed the reverse engineering of the human brain. $1,000 of computing will be far more powerful than the human brain in terms of basic raw capacity. Computers will combine the subtle pattern recognition powers of human intelligence with ways in which machines are already superior in terms of doing analytic thinking, remembering billions of facts accurately. Machines can share their knowledge very quickly. Human life expectancy is expanding. It was 37 in 1800. And with this sort of biotechnology and nanotechnology revolutions, this will move up very rapidly in the years ahead. My main message is that progress in technology is exponential, not linear. Many, even scientists, assume a linear model, so they'll say, oh, it'll be hundreds of years before we have self-replicating nanotechnology assembly or artificial intelligence. If you really look at the power of exponential growth, you'll see that these things are pretty soon at hand.